Hello, hi, and good evening. We'll just start the session. So, I think only two more sessions are left, right, in the course tutorials. So, in the last two sessions, we will not be seeing any concepts as such, new concepts, but we will try to see some previous year problems. So, if you have registered for the exam, so that they can be helpful for you guys. Okay. So, most of these previous year problems happen to be kind of theoretical based multiple choice questions. Okay. So it may be a little dry, but I think it will help you in your exam preparation. Okay. So we'll just start. Hi. So am I audible?
Sir, you're right.
Okay. Okay. Thanks. I will just share my screen and we will just start. Okay.
போடு போடு ஒரு
Okay, yeah, sorry, it was muted kind of. So I was asking you, what is a motor drive? Do you know? So what kind of drives the motor? So what is the converter that kind of drives the motor? So let's say I have a battery. Okay, let's take a practical example. I have 72 volts battery. Okay, so I wanted to drive the propulsion motor of a two-wheeler. Okay, or a three-wheeler. Okay. So what is the interface, or what would be the interface that kind of enables you to connect a 72 volt DC battery to drive, let's say, a PMSM motor, right? Permanent magnet synchronous motor. So what is the power electronic converter that you would have that would enable you to drive the motor from a DC battery? Right. So the answer is you have the battery, okay? And after the battery, what you will be having is an inverter. Okay. So the inverter would be kind of a PWM inverter wherein you will do what is known as a sinusoidal PWM, right? You would have studied about it. There are even advanced techniques of doing this using other PWM techniques, such as space vector PWM and so on. But let's say for now we are using an inverter that works on sinusoidal PWM. Okay. So you have the battery, you have an inverter, and then you kind of connect the shaft, uh, or you kind of get the three-phase AC pulses or the AC voltages from the inverter, which is then connected to the terminals of the motor. Okay, so this is what constitutes a motor drive. So if someone tells about a motor drive, you should think about this particular component, which is the inverter. Okay. So over here, based, I'm not writing the other options as such, but the answer would be something like a motor integrated with the drive system and other components like encoders and controllers. Okay, fine. So I hope you got the answer. Like, I mean, all of these are theoretical quiz problems. Okay, so that's why I was telling it may be a little dry, but this is helpful for your exam. Okay. So the next question is, why at all do we go for motor drives? Right? That is, okay, so we have an integrated motor drive wherein we have the battery, inverter, and then a motor. So the idea is that this inverter is within the vehicle. Okay. So if you have a two-wheeler or something, right? So all of these systems are within the vehicle. If you kind of open the belly region, so you will be able to find the battery, then the inverter and the motor. Okay, all of them will be housed properly. So why are we using this? Why can't we just have the motor and kind of connect externally, right? So that's the next question. So the idea is that if you are having all of this integrated into one system, you kind of save space. Okay. So the advantages are as follows. So the advantages would be um, reduce cabling and wiring. Okay. And lower installation costs. And three would be space saving capability. Okay. Fine. So, should I wait over here? I'm not sure. Are you noting this down some or something? Because I think it would be better if you can note it down or you take screenshot of this or something. Okay, because what I'm discussing is basically previous year's problems, so it would be helpful for you. Okay, so can I move ahead?
Sir.
Okay, fine.
And one
So
doubt.
the next question, yeah, yeah, sure, sure.
Yeah. In exam, we have to type these all the advantages. They will ask the questions
No, 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 no.
like
It's not. It's not like typing. So the questions over here are something like,
MCQ type
which of the
questions only.
following is not? So the question was, which of the following is not an advantage of integrated motor drives? Okay. So there are four options. All right.
Yeah.
Okay. The answer that is that is not an advantage is something like it doesn't have good performance in harsh environments and so on. Okay. So I'm writing these so that we go through the process, like, or else I can directly show the problems also. Like that is one thing, but I thought like it would be good if we slowly go through it so you can also internalize it.
But we got a mail, but they have said that questions will be filling the blanks, essay type answers. So that's why I asked.
Oh, okay. I'm not sure about what you get in the exam, but this is based on previous year's assignments and the final exam. Okay. So I'm not supposed to directly share the PDF over here, so that's why I thought like this is a good way to kind of go through the problems. That is one by one. So this particular thing was one problem. What is an integrated motor drive? There are four other options. Okay, I mean three other options. So the correct answer is something like this: motor integrated with the drive system and other components like encoders and controllers. So if you see the other options itself, like you can directly eliminate them. Like the questions are like that only. Okay, it's not that you should mug this answer up and go, or you should remember this. If you see the other options, they are like totally off. Like they are not related to motor drive at all. So from that itself, you can understand that this is the correct answer. Okay, the questions are like that only. It's not like some three, four options are very closely related and you have to think a lot or something. Okay. I mean, this is kind of simple only. All of these I think you can easily tell, right? Like if it is integrated together, you know that there is going to be reduced cabling and wiring because I told that all of these are housed together in a single enclosure. Okay, because the entire IMD integrated motor drive is housed together in a single enclosure. Okay, so the connections are kind of very compact and very small. So from there itself, you can understand because it is integrated, it wouldn't have very long wires and cables. One. Second, there would be space saving capability because obviously it is all integrated together. Okay, so I mean, kind of you can directly eliminate the other options. So the questions are like that only. Okay. Okay. So as I was telling, one of the challenges of IMDs are okay. So let's look at the challenges. All right. So if we go towards the challenges of IMDs. Okay. So one of the predominant challenges is regarding the uh, operation in harsh environments. Okay. So for instance, we can operate it in two-wheelers and three-wheelers. But you would have seen that, let's take practical examples. You would have seen an electric auto rickshaw, right? Or let's say an electric bike. If you go and buy an electric bike, they generally tell that you cannot use these electric bikes or whatever. I mean, you would have also seen delivery persons using electric bikes, right? So if you want to buy these electric bikes, they would tell that it can support a maximum slope of up to, let's say, around 30 degrees or so. Okay, it means that you cannot use these electric bikes beyond that angle. Okay, so let's say you are climbing a bridge, over bridge, right? So over there, the angle is expected to be around somewhere around 10 degrees, 20 degrees or so, right? Not more than that. But if you go towards hilly terrains, right, wherein there can be steep slopes, okay, more than 30 degrees or 40 degrees, over there, you cannot use these e-bikes. Can you tell me why? Do you understand the problem? So the same electric bike that we use, let's say you may have seen in your cities or uh, used by delivery persons, they can be used for local kind of transportation, right? But you cannot use them for, let's say, going on a ride to the mountains, right? So why is it so? Why do people prefer vehicles like, let's say, Royal Enfield or so? Why can't we use these e-bikes, right? So what happens is if you go for more and more slope, right? If you have driven a bike, you will know. Like if you want to go for more and more slopes, in order to maintain the same speed, right, you would need to accelerate even more. Correct? That is, you will need to press the accelerator even more so that you are able to climb that much ascent, right? Climb that much slope. So what happens is if you try to give more and more acceleration, it means that you are trying to increase the torque of the motor, right? So you have the motor, and if you want to go for more and more acceleration, you want to increase the torque, right? And you would have studied when you studied about electrical machines, right? That if you want to increase the torque, you have to increase the armature current, right? You would have studied that the torque is directly proportional to the armature current. So if you want to get more and more torque out of the motor, you have to have more and more current going in the armature windings, right? So if you want to push more and more current, obviously that current has to be coming from the inverter and indirectly from the battery. Okay. So that is why they generally tell that it can support a maximum slope up to this much, not more than that. Why? Because if you go for more and more slope, more and more torque is required. Therefore, more and more current is required. So one of the challenges of IMDs is that you cannot kind of operate it for high torque applications. Okay. So one of the main challenges of IMDs, right, is that it has a limited horsepower for high torque applications. Okay. So if you want to use the same vehicle for high torque applications, I mean your motor has to be rated for more and more power. Okay, that is more and more current, right? And second is that it cannot be used for harsh environments. Okay, cannot be used in harsh environments like refineries and mills. Okay, so this is one of the challenges. That is the limited horsepower for high torque applications. Okay. Okay. Fine. So these are just some general points about IMDs. Okay. That is, we saw the definition, right? And we saw some advantages and we saw a few challenges. Okay. So we'll move on to the next part. Okay. So the next question would be, which WBG or wideband gap device, which WBG device is mentioned as a switching option for integrated motor drives? So A, SIC, MOSFETs, B, IGBTs, C thyristors and D bipolar junction resistors or BJTs. So which is the correct answer? Can you tell? Which of the following is a WBG device for IMDs for integrated motor
The
drives?
C was
Yeah. So pretty simple, right? Like all others are not WBG devices itself. So you can directly find out the answer. Okay. So next question would be um, what is the primary benefit of using WBG devices in IMDs? Okay, so why do we use WBG devices? So, I mean, the options are all very simple. Okay, increase component cost. Okay. So, which is the correct answer?
option B.
Yeah, right. So, seeing the options itself, you can directly tell. For this, you need not study anything, right? Simple only. Okay. So, the next question is the exact opposite. So, what is the challenge? Okay. So, which is the correct answer for this? Oh, so, what is the primary challenge? So, which is the correct answer? Selvakumar sir and others. So, what is the challenge of using WBGs? So, WBGs, do they allow reduced switching speed or can we go for high switching speed? So, we can go for high switching speed with WBG devices. Okay, so A is not the answer. Second is cost and thermal management. Yes, this is the answer because WBGs are costly, number one. Number two, in terms of the size, right? WBG devices are very small compared to Other devices, WBG devices, are very small. So you imagine that the entire heat dissipation has to happen in a very small area, right? So if the area of heat dissipation is smaller, then what happens? The temperature would get kind of concentrated, right? So temperature gets kind of concentrated over there and the temperature builds up rapidly. So this is a particular concern, okay? That is cost and thermal management is a concern, right? It is the challenge of using WBG devices, okay? So is this fine so far? Can I move on to the next topic? This is about just IMDs. Sailokumar sir and others, like, can you please tell if this is fine or should I wait or something? Okay, sure, thanks. Okay, so next we will move towards another set of problems wherein we see the application of WBG devices towards renewable energy. Okay, towards renewable energy systems. Okay, so the first question is very similar. What is the primary benefit of using WBGs in renewable energy systems? Okay, so what is the primary benefit? So the options are higher energy storage capacity, right? High voltage blocking. Okay. So can you tell me what would be the correct answer? What is the primary benefit of using WBG devices in renewable energy systems? So would it be higher energy storage capacity, high voltage blocking capability, and low switching losses, lower manufacturing costs, or compatibility with older systems? So sorry. Yeah. So definitely compatibility with older systems is not the answer, right? And we just saw that WBG devices have higher cost. So definitely option C is not the answer. Okay. And another thing is, see, these are devices. Devices cannot store energy, right? So you cannot have higher energy storage capacity and all, right? So WBG devices are not some batteries where you can store energy. Okay. So the idea is that WBG devices can support very high voltage blocking capacity. Okay, and this is something that we need for renewable energy systems, wherein the voltage that you would build up would be in kind of kilovolt level. Okay, and of course there will be lower switching losses. So the answer is this. Okay, I mean these are very simple questions, right? So the next question would be, which renewable energy system primarily benefits from WBG devices? Solar and hydroelectric, photovoltaic. Okay, so can you try to tell which renewable energy system primarily benefits from WBG devices? Will it be solar and hydroelectric, or is it PV and wind energy systems, biomass and geothermal, nuclear and tidal energy? Right. So, yeah, correct. So the answer is answer B. Okay. So the reason is that, see, if you see the operation of PV systems, right? So if you see the characteristic of a photovoltaic cell, so there is something called as a maximum power point, okay, for a PV cell. That is, if you operate at that point, you will be able to get the maximum amount of wattage from each PV cell. So the idea is that to have a converter which will enable you to operate all the PV cells at the maximum power point. Okay, and what people do is you get the voltage outputs from each PV cell and you kind of connect the entire network in kind of a series parallel fashion. Okay, and then what they do is they boost up the voltage using a boost converter, right? So they boost up the voltage and then they will interface with a common DC link. Okay, so you have a boost converter over there. Mostly if you see, there would be a boost converter interfaced after the PV array. Okay, and once you get the common DC link, you can always use it for other applications. That is, if you want, you can convert it into the 50 hertz AC and so on, right? So that is one, right? And a similar system is also used for wind energy, right? So yeah, so the answer is photovoltaic and wind energy systems, right? So let's move on to the next question. So this is another simple problem. Okay, I mean all of these are very simple only. So the answer is silicon or hybrid MOSFETs, and then SiC and GaN, silicon carbide and gallium nitride, and then vacuums. So I think this everyone is pretty aware that the answer is going to be SIC and GAN. Okay, right. So the next question is, what is the main goal of using WBG devices in RES? Reducing the voltage, increasing system complexity, okay, enhancing power capacity and efficiency. Right, so again, very simple question. So idea is to enhance the power capacity and efficiency. Okay. So the next question is, I'm going a little fast over here because all of these are very simple questions. Okay. What is the key feature of WBG devices? Okay. That makes them attractive for renewable energy systems. So what is the key feature? So one is high thermal resistance. Okay. So I think this also, the answer is ultra fast switching speed, right? Okay. So so the next question, which I'm not typing, is what was the main challenge identified in using WBG devices in renewable energy systems? So the answer is again increased material cost and thermal management, right? So this is something we have seen earlier also, right? So primary challenge of using WBG devices is cost and thermal management. So here the answer is increase um, material cost and thermal management. Same thing. Okay. Fine. Again, another question is why WBG devices are suited for uh, large rated power converters in renewable energy systems. Okay, so the answer is again they offer significant power capacity and significant efficiency improvement. Okay, so all others are like not the okay. I can just write. Okay, so the answer is they offer significant efficiency improvements. Okay, though they are costly and complex. Okay, they offer significant efficiency improvements. That is the idea. Okay, so the next one is which of the following, which is a key feature of SIC devices in renewable energy systems. Okay, so the answers are high level operating temperature, so which is the correct answer? Again, I think this is very easy, right? So which of the following is a key feature? So it has high LOL operating temperature. Okay. And second thing is, yeah, correct. So second thing is SIC devices have higher voltage blocking capability than GAN. Okay. So commercially also, if you see GAN is available only till around 650, 700 volts. Commercially, mostly. Okay. Whereas SIC devices are generally rated for upwards of even 900 volts, 1200 volts, 1700-volt SIC devices are there. Okay. And in the lab, people have even got 3.3 kV rated SIC devices. Okay. So SIC always has higher blocking capability than GAN. Okay. And the other two are not even close to correct answer. Okay. Okay. So I think the last question, no, we have two more questions. What is the So what is the correct answer for this? Correct. So it provides a cost-effective solution with high efficiency. Okay. So the last question in this would be question number 9. Okay, I just open it. It provides a cost-effective solution with high efficiency, and yeah. So the last question is, what is the main application of the two-level back converter? Controlling the speed of electric vehicles, optimizing energy distribution in a microgrid, and conversion or doubly immune systems. So battery life. So what is the correct answer? Correct. So two-level back-to-back converter is mainly used for WFED induction generator. Okay. Okay. So if this is fine, we will move on to the next set of problems. Okay. We have seen motor drives and we have seen renewable energy sources, right? Just hang on a second. Okay, so I think I missed two problems in IMDs. Okay, so just cover it up. So one of the problems in IMDs was which application area was highlighted for IMDs using WBG devices. Hydrostatic actuators. So what is the answer in your lecture slides? Did you go through it? What was the application area that was highlighted in your lecture slides? So this is based on the lecture slides, okay? I'll just type the next question. Okay, so the answer is you went through electrohydrostatic actuators. Okay. I mean, knowledge also can be the option, but point is C. Um, wireless communication systems, we are not dealing with them, right? And solar power inverters do not have motor drives, right? Solar power inverters do not require motor drives as such, right? So that's a static kind of power conversion systems, right? So the answer is with electrohydrostatic actuators. Okay, so actuators, as in like from that itself, you can understand there's going to be a mechanical to electrical energy conversion, right? From the term actuator itself, you can understand. So from there itself, like you can tell the answer is A because there is actuator. Okay. Which type of IMD mounting attaches drive radially to the housing? Radially stator. So what is the correct option for this? Very simple. Like from the question itself, you can tell the answer, right? So what is the correct option? So in the question itself, you can see that is radially, and in the question itself, there is you can see housing. So from the option, you see that the answer is going to be this, right? Correct. Okay. So did you get it? Especially question number 5. IMD is using WBG devices. So if it is motor drive, it means that definitely there has to be a motor, or in a sense, there has to be electrical to mechanical or mechanical to electrical energy conversion, right? So in solar power inverters, you know that there is no moving mechanism as such, right? Because there is just the PV, then boost converter, and then inverter. So solar power inverter is basically PV, then there will be a boost converter, and then there will be inverter. Okay, this is the chain for solar PV. So over here, you see that there is no um, motor drive stage as such, right? There is no motor as such in this, no moving part. So wireless communication system, definitely not the answer. right? So the answer is electrohydrostatic actuator, because actuator means there is a mechanical energy conversion, right? So from that itself, you can understand the option. Okay, fine. Okay, so last question in IMD. Okay. So the last question in IMD is, so which network protocols? So can you tell which is the correct answer based on what you have gone through in the lectures? Correct. So Ethernet IP, EtherCAT, and CAN open. Okay. Yeah, I think this was question number 7. Right. Okay. So we have seen all the problems in IMDs and also in the renewable energy systems. Okay. I think IMDs and renewable energy systems are your week 11 and week 12 respectively, right? Okay. Okay, so I hope this is fine, right? Then we can go ahead with questions on. So WBG devices we have seen for IMDs. We have also seen WBG devices for renewable energy systems. So next we will move towards PCB design, problems on PCB design. Okay. Okay, so by the way, for this week and next week, we will be seeing all the previous time questions. Okay, so it will mostly be these kind of questions only that have come previously. Okay, so we will be doing all of those questions. Okay, it will help you for your exams. Okay, so I have done. I have to start PCBs now. So this would be PCB design. Okay, so corresponding to week 10, I guess, right? So PCB design. The first question is, what are the basic steps PCB design and manufacturing? Okay. Oh, probably here both of these are highlighted. Okay. Yeah. So what are the basic steps of PCB design and manufacturing? Okay. So the first flow is schematic design, then PCB layout and rubber generation. Rubber generation, PCB layout. I think this is very simple. So can you tell what is the correct answer? What are the basic steps? What do you do? What is the step for PCB design? So you have three steps in that, right? So correct. So first you will do the schematic, right? And I think KiCad was taught, the KiCad software was taught to you guys. So first you do the schematic and then you assign the footprint for each of those schematic symbols, right? So you use symbols. So if you have a MOSFET, you will use a MOSFET symbol in the schematic, wherein you tell that, okay, this is how the connection looks like. Okay, so if you have to make a half bridge, you will kind of connect the drain terminal of the top device to the DC source, and then you will connect the source of the top device to the drain of the bottom device, right? So that's how you make the connections. And after you make the connections in the schematic, you will assign the footprint, right? So if you have, let's say, a TiVo package device for MOSFET, so we'll tell that, okay, there will be 3 holes in the board, 3 holes in the power board, corresponding to the 3 legs, drain, source, and gate. And then you will export it to the PCB and you will do the PCB layout, right? That is how the connections are going to look like actually on the PCB, right? And after that, you will create the Gerber file, and what you will give to the PCB manufacturer is only the Gerber file. Okay. So this is the workflow, that is schematic, then PCB layout, and then Gerber file. Right? Okay. So the next question is, what should be the track width from driver to gate of the space part? So what should be the track width is the question. Okay. So that is driver to switch gate So I'm denoting track width as TW, okay, just for my convenience, okay. So driver to switch gate track width should be more than our loop track width, or driver to switch gate track width should be less than for loop track width, or should it be equal? Should it be equal or none of the above? So which is the correct answer? So what about the track width? Which should be thicker? Should your cover loop be thicker or should your gate loop be thicker? Or in other words, which should be smaller or thinner? Which should be as small as possible? Should your cover loop be small or should your gate loop be small? What should be the track width, right? Or you think in this correct? So you think in these terms, which of these would follow more, would kind of allow more current, right? So you know that power current is going to flow through the power loop, right? Like let's say around 30 amperes or 60 amperes is going to flow through the power loop. So obviously the power loop can be thicker. Okay, it needs to be thicker. Or in other words, the gate in the gate loop side, the current is going to be very, very small. And also, you know that MOSFET is a voltage control device. Unlike BJT, you need not continuously give some current to the gate, right? You just need to give current when during turn on and turn off. So that's why the track width for the driver to switch gate is lesser than the power loop track width. Also, you want to have the parasitics in the gate loop to be as small as possible compared to the power loop. Okay. So that is why the answer is B. That is the driver to switch gate track width should be less than the power loop track width. Okay. So the next question is so which layer of a PCB is responsible for providing electricity? This is very, very simple. So what is the answer? I think the answer is also highlighted correctly. So which of these provides electrical connections? The answer is obviously the copper layer provides electrical connections, right? So in PCB design, sorry, which material is typically used as the substrate in standard PCBs? A copper, aluminium, C R4, and D silicon. So what is the answer? What is the substrate in PCBs? Is it copper, aluminium? Correct. It is answer C. That is FR4. Right? All PCBs are typically made up of FR4 substrate. Okay. There are also other PCBs. So standard PCBs are mainly made up of FR4. There are also other PCBs. If you go to a PCB manufacturer website, you can see, right? Many PCB manufacturers provide you options with different substrates. Okay. FR4 is standard, right? But you have other PCBs known as metal core PCBs, right? So there are a lot of options as well. Epoxy and so on. So yeah, so the next and the last question with PCBs is this: which material, sorry, in PCB design, what is the term for the electrical path that connects two or more as components? Is schematic, ground plane, none of the above. So what is the answer? Again, a simple question only. So what is the term for the electrical path that connects two or more pads or components? So what is, with what do you connect? Correct. So you use a trace to kind of connect. Trace, or we can also have copper pores. Okay, so there are copper regions, right? You can also create copper regions, or you can use trace. So we call it copper regions or copper pores. Copper pores or copper regions. Okay. Right. So this is it about PCB design questions. Okay. All of these are very simple. Okay. Fine. Okay. So just give me a 5-minute break. I'll come back and we will see some questions on power density. Okay. Yeah. So I'll just have some water and come back. Okay. So we will see questions on power density, and in the next week we will be seeing questions with EMI. Right? You went through EMI also in past lectures. So there are some questions with EMIs and crosstalk and so. Okay. Okay, thanks for hanging around. I'll just start. Okay. So we will see some questions on power density and then we will wrap up for the day. Okay. So questions on power density. Okay. So the first question is the simplest question. So what is power density? Right. So the options are power per unit voltage, power per unit volume, power per unit um, area. So what is the correct answer? Very simple, right? So the answer is power per unit volume. Right? That is your correct power density. Okay, so the unit would be something like in SI units, it is watt per meter cube. Okay, okay, watt per meter cube, or people also write it as kilowatt per liter. Okay, this is a very famous notation in for power converters. Okay, SI unit is watt per meter cube, but in power converters or in power electronics, so we generally write it in terms of kilowatt per liter. Okay, so in power electronics we write it as kilowatt per liter. And people use kilowatt per centimeter cube, kilowatt per meter cube, and kilowatt per inch cube, or so on. Okay, but this is the idea. Power density is power per unit volume. Okay. Okay. So the next question is, how do we increase the power density? Right? How can power density be improved? Right? By increasing size of passive components. Passive components, they mean the filter inductor and filter capacitor, right? That is your passive components. Passive components means filter L and C. Okay, and by increasing switching frequency, so what is the correct answer? How can power density be improved? Yeah, correct answer is option B, right? Because as you know, what happens is if your switching frequency increases, right? That is your Fs increases, right? Your Fs increases, then your L and C will decrease, right? Right? So if your Fs increases, your passive size reduces, okay? Because the requirement of uh, your L and C will decrease. If you remember how to calculate or how to compute the filter inductance and filter capacitance for a buck converter, right? You would have studied in the formulae that your L and C, right, are directly proportional to the or inversely proportional to the frequency, right? They are inversely proportional to the switching frequency. Okay, so over here I would like to tell a very good analogy. Okay, that is something my professor taught me over here. Okay, So I think this will give a very good perspective. Okay, so let's take a very practical example, right? So so let's say you have one bucket full of water. Okay, so this is your bucket one, and so this is full of water. All right. So what you want to do is actually you want to transfer this water into another bucket. Okay, the same amount of water you want to transfer it to another bucket. Okay, so you want to somehow um, take the water, right? So you want to take the water from here to here. Okay, and thereby you want to fill it. So this is what we want to achieve. Okay, that is we want to fill bucket 2. Okay, and I give you two options, right? So I give you two options. So that is, one is I will give you a large mug. Okay, so I will give you a large mug with a handle. Okay, so I will give you a large mug like this. And the second option is I will give you a smaller mug. Okay, so with the large mug, let's say you have to take the water 5 times. Okay, you have to take the water 5 times, and if you do it 5 times, like if you take the water 5 times, you will eventually empty this bucket and transfer the entire amount of water to the second bucket. This is one. And in the second case, you can use the bucket 50 times. I mean, you can use the mug 50 times, and in 50 times you are able to transfer the same amount of water from bucket 1 to bucket 2. Okay, right? So you tell me, among these two options, which is easier for you to carry, right? So which is easier for you to carry? Is it easier for you to carry the first mug, or is it easier for you to carry the second mug? It is obviously easier for us to carry the second mug, right? That is, I will have a smaller mug, right? I will have a smaller mug. And what I will do is I will continuously take water away from bucket 1 and put it into bucket 2. Okay, I have to do it multiple amount of times, right? To transfer the same amount of energy. I can do it multiple amount of times, but the idea is that with the second mug, you can do it faster, right? With the second mug, you can do it faster, and you're doing it faster, so you will obviously need to do it 50 times, but the point is that you will be able to do it faster, right? So over here it's faster and over here it is slower. Okay, so same analogy you apply to the converter. So what is your power converter? Power converter is basically an interface, right? So you have, so let's say you take a buck converter, right? So in a buck converter, you have a DC battery at the input, right? And then you have a switch over here, you have a diode over here, right? And then you have L, C, and then you will have the output. Okay, so you think of it as something like this. Okay, so this is your power conversion stage, this switch and then L and C. Okay, this is V1, this is V2, or this is your bucket 1 and this is bucket 2. Okay, so you want to transfer energy from one battery to the other battery at the load. Okay, from V1 to V2, right? And what you have is, this is the power conversion stage. And how are you doing power conversion? You are using energy storage elements like L and C, right? Basically, you are using energy storage elements. So the idea is, So over here, mug is the water storage element, right? Similarly, you apply the same analogy over here. Your L and C are your energy storage elements. Okay. So you can have smaller values of L and C and do it multiple times, and you can kind of switch faster, right, to transfer the same amount of energy. Or you can have large values of L and C, and you can do the power. You can kind of operate it slower. Do you get it? Like, are you able to follow how I am relating this L and C to the mugs over here? You can either use a bigger mug, right, and do it lesser number of times, okay, or you can use a smaller mug and do it more number of times. So this is something like you can use higher values of L and C, okay, large L and C, so lesser switching frequency, or you can use smaller values of L and C and go for more switching frequency. Are you getting the analogy? Why we tell that, okay, if you have large values of LNC, you can go only for lesser values of switching frequency and so on. Is this fine to both of you? Okay. So that is why in this question, how can power density be improved? By increasing the switching frequency. If we increase the switching frequency, or uh, switching frequency increases means your L and C values are going to decrease. That is, it is like you're going to use smaller mugs. So if you use smaller power conversion stages, the size also decreases. That is the idea. Okay. Okay. So power density can be improved by increasing the switching frequency. Okay. So the next question is, what is, this is again the same problem, same question. What is one benefit of increasing switching frequency? So what is the answer for this? The answer would be A, right? That is smaller inductors and capacitors. If we increase the switching frequency, we just saw more switching frequency, smaller would be LNC, smaller LNC. Okay. That is, you need a smaller mug. You can do it multiple times, more number of times. Okay. Okay. Fine. So can you tell me about the current ripple? So if I have a fixed value of L, right? I have a fixed value of inductance. What happens to the current ripple? So the question is, so I have a fixed value of L. Okay. The L is fixed. All right. So what about a current ripple? And I will give you two cases, right? So I have a fixed value of L. Okay. And in one case, switching frequency is, let's say, 10 kilohertz. Okay. And in the other case, the switching frequency is 100 kilohertz. Where the current ripple will be more? Will it be more in the 10 kilohertz case or 100 kilohertz case? I have given you a fixed value of inductance. Okay. So your inductor current, you may know, your inductor current is going to look like this, right? In steady state, your inductor current would be something like, and so on, right? So this is your inductor current, and this is your dTs period, and this is your Ts period, right? So can you tell in which case your ripple will be more? So the question is, this is the peak to peak ripple, right? So this is the peak to peak ripple. I will call it as delta IL. Okay. So delta IL is your peak to peak ripple. So, and I have given you two possibilities. One is 10 kilohertz and one is 100 kilohertz. For the same duty, right? And same inductance, where the ripple will be more? Will it be more in 10 kilohertz case or will it be more in 100 kilohertz case? Can you tell? Okay. See, the point is, if your inductance is fixed, right? If your inductance is fixed, it means your slope of current is fixed, right? That means if your inductance is fixed, your slope is fixed. So you will see that for the 10 kilohertz case, right? If it is something like this, so let's say uh, for 100 kilohertz, the switching period is 10 microseconds. Okay, switching period is 10 microseconds. So this is 10 microseconds. Let's say this is 5 microseconds. Okay, so for 5 microseconds it will increase, for 5 microseconds it will decrease. Okay, and the slope is kind of like this. Okay, now for the 10 kilohertz case, which means the switching period is 100 microseconds, right? In this case, what you will see is that it would increase and decrease like this, right? So for 50 microseconds, it will keep on increasing. Okay, for the same slope. That's why I told, if you have the same inductor, you have the same slope, right? For the same inductor, you have the same slope. If the slopes are same, then in that case, you see that over here, the rising slope is only for 5 microseconds in 100 kilohertz case. But in A case, that is in 10 kilohertz case, the rising slope is for 50 microseconds, right? For 50 microseconds, the inductor current will keep on increasing. That is why you will see that the peak to peak ripple delta IL for 10 kilohertz is more than delta IL for 100 kilohertz. Because in 100 kilohertz case, you are not allowing the inductor current more time to rise. Okay, you are not giving the inductor current more time to rise. Okay, whereas in the 10 kilohertz case, right, that is where you have a huge time period, right, that is 100 microseconds. So you are giving the inductor current more time to increase. Are you understanding this? If you have any doubt, please write in the comment section. Okay? I mean in the chat box. Okay, that is, if you go for lesser switching frequency, if you go for lesser switching frequency, you are having more time. Okay, more time means you are allowing the inductor current to rise more and fall more. Okay, that is why the ripple, peak to peak ripple is going to be higher, right? Do you understand this? You are allowing more time for the inductor current to rise. you compare over here, you have 5 microsecond, this is 50 microsecond. Okay, so it is going to increase 10 times more. So the ripple will be 10 times higher. Are you able to follow what I'm telling? I don't know if I'm there or not. Okay, great. Yeah, so as I was telling, the ripple will be more for lesser switching frequency because you are allowing more time for the inductor current to increase. Okay, more time for the inductor current to increase. Right. So that is why if you increase the switching frequency, what will happen? Actually, if you increase the switching frequency, if you go for higher and higher switching frequency, so higher FS means lesser time, right? So lesser time means lesser ripple. Okay. So the idea is lesser ripple. So you will not get higher current ripple. In fact, if you increase the switching frequency, you will get lesser ripple. Okay, you will get lesser ripple if you increase the switching frequency. Okay. Okay. So again, a very related question. So the relation okay. So what is the relationship between inductance and switching frequency number converter? So what is the relationship between inductance and switching frequency? Is it directly proportional? Directly proportional, and option B, inversely proportional. Option C, independent of each other. So they are independent, and option D is inductances proportional. So what is the answer for this? What is the relationship between inductance and switching frequency? So as your inductance, we just saw this, right? Like as your frequency increases, if you go for higher and higher switching frequency, the size of your L and C are going to decrease. The size of your passive components will decrease, right? Correct. So it is going to be inversely proportional. This is the answer. Okay. So as if you are operating at low switching frequency, you need a high inductance. Why? Because if you don't have sufficient inductance, then you will get huge ripple. We just saw it, right? If you have for 10 kilohertz, the ripple is more. For 100 kilohertz, you don't give it sufficient time. So the inductance current will not rise too much. Okay, you will get an average value over here. But if you go for lesser switching frequency, you get more time. So the current will rise even more. If you want to restrict the current rise, you have to put a larger inductance, right? You have to use a larger inductance. So it is directly, I mean, inversely proportional. Okay. So it is inversely proportional. Okay. So I think till this point we can stop for the day. Okay. Another 6 questions are remaining in power density. Okay. So we will continue it in the last class. Okay. So in the last class, we will see remaining questions on power density one, and then few questions with some EMI and LISN that you had done previously. Okay. So yeah, we will do that from the next week. Okay. So any other questions or is this fine? Shall we close for the day? Okay. Okay. Thank you very much for attending, all three of you. Yeah. Yeah. Thanks very much for attending. Okay. So we'll close for the day. We will make in the next week. That will be the last class. Okay. We will see the remaining questions, and I think this would these are the questions that were provided as part of last year's question set. Okay. So I think if we see that, it will be good. I will also upload these slides, so go through the slides also. Okay, from your exam perspective. Okay. Thanks everyone, and good night. Have a great week ahead. Yeah. Bye.